the last homework of the semester. Look, I can make myself squish around. I'll stop that. And this is homework 24 and impulse momentum problem with collision here. So we have this slender rod that's 3 feet long and it weighs 10 pounds and it's dropped from a height of 1 foot. The angle as shown is 60 degrees, and when it strikes the ground, or just before it strikes the ground, it's not rotating. The coefficient of restitution between the rod and the ground is 0.6. We want to find the translational and angular velocity of the center of the rod after the collision, and we want to find the efficiency of the collision. So I've written this thing out, and I've actually solved it already. So hopefully I got all the bugs out of this. So we could do this a couple different ways. It's starting from rest here at a height that's like 1 foot away from the ground. And it's going to drop, right? So it's just going whee, and it's going to go boink, boink, boink. You know, it's going to go boink, and it's going to rotate. So I'm going to use work energy to find the velocity just before it strikes the ground, and I will call this state 1 right here at the beginning, and this is state 2, and then state 3 is going to be just after the collision right there, right? So can't remember. Do I start with a KE or PE? I can never remember. Or at this point in the semester, it should just be automatic, right? So the datum is going to be at the bottom right there, right? So I'll just cross that out. And it's starting from rest, and there's no external things going on right there in between states 1 and 2. So what we really have is the potential energy, which we know is going to be mgh is going to be equal to 1/2 mv2 squared right there, right? And notice that the mass cancels out. We could have also done this with kinematics, right? We could have done this with just like, you know, a simple projectile motion problem, right? Because we have a distance and we have the acceleration, which is gravity. But anyway, we have 32.2 times 1 foot and 1/2, and so we have the velocity at the second point right there. So we find the velocity of the center of mass. That's an important thing. Maybe I should have written out the center of mass in there, but whatever. We end up getting that it's going to be 8.025 feet per second. Right. Now, I'm trying to decide how I want to handle this. We could do the collision, right? So the coefficient of restitution. Now we got to remember this is a infinitely large mass and has 0. So infinity times 0 is who knows. So that's the kind of problem it is. So if I write out the coefficient of restitution like I usually like to do, I usually go V. Trying to think of what I want to write onto there. VA. Let's say 3 minus V. Let's see. I'm going to write the ground. Let's see. I guess a GR for the ground, right? GR3 is going to be VGR2 minus VA2, and in this case VA2 is going to be equal here because it's not rotating, so the center of mass has the same velocity as VA is equal to the center of mass. It won't always be, but because this thing is translating without rotating, that's true. Now we know that the velocity before and after this right here, so what we find is we get the velocity of A3 is just simply going to be negative E, right, times the velocity of A2. So we have the velocity of A3, and the negative is just telling us it's going to be going upwards, right? So we don't, so we could even have said that this was a negative velocity, and then we put it in there so it turns into a positive value. I'll put the negative in there, but it doesn't matter. So we got 0.6 of the coefficient of restitution, 8.025. So we get a negative 4.815 feet per second. All right, so we know a few things. We also need to know some kinematic relationships between the center of mass versus the center of point A. So we know the velocity of A after the collision, but we don't know the center of mass, the velocity of the center of mass. And that's what all the calculations get based on, is the center of mass. So we need to do kinematics and a velocity analysis, right? So I'm going to do 3 diagrams right here. And so I kind of made them sloping upwards. So I'm going to say that it's equal to these things. So we know the velocity of this guy right here. This is VA3. We want to find the velocity of the center of this. Am I saying that correctly? I think I am. And one thing I didn't show yet, but I should kind of show, is that the velocity. This is interesting because the velocity of the center. I don't want to think about it too much. I gotta get this stuff done. Okay. So anyway, this is the velocity of CM3. And we're going to look for the velocity of CM3. I'm trying to think about whether it has any horizontal component to it, and I think it kind of has to, but I'll show you in a minute where it can't. So I'm a little bit stuck on that. But anyway, we'll just keep on moving with this. All right, so we want the velocity at the center of mass to the thing. And I'm going to assume it's going to rotate counterclockwise. And this is why I'm saying that I think it has to have some amount of velocity in the x direction, because we know that we're going to have, this is the velocity of CM with respect to A. We might even call it 3 right here, right? And so in the y direction, or I should write out the equation, that the velocity of the center of mass, 3, is going to be equal to the velocity of A3 plus the velocity of CM with respect to A3. And we know that that's going to be omega 3 times 1/2 of the length right there. But in the y direction, we're going to say VCM3, and I could put it as y if I wanted to, is going to be equal to, I don't like that minus sign. I'm going to get rid of it. I don't like it. I don't like the minus sign because it is going upwards, right? So because initially it was going downwards. So I could actually, if I just go like this, minus, that shows me, okay, that would be correct, right? Yeah. 4.815. Yeah, I hadn't put it in there yet. Minus, and here's where I have to mess with some angles right there, right? So here is that. This angle right there is the same as that angle. So this is going to be omega 3 times my length of this thing, which we will say is, it's 3, right, divided by 2. That's the length right there. But now we need the cosine of 60 degrees. This turns out to be 4.815 minus, and I think that goes 0.75, right? Because that's 1.5, and the cosine of 60 is 0.5, so I think it's 0.75 omega 3. That's a good relationship for us. The x terms right here, it's going to be interesting. Maybe we should just call this in the y direction. VCMX. Yeah. Concerned by this. Let's go VCM3X. Yeah, 3 in there. Yeah, I'm going off script because I didn't write it over before, and my source of this did not include it, so I don't know. Trying to think about whether I want to or not. We had to decide. I think this has to be 0, but that has an x component to it right there, right? And I show this in a negative direction here because I know that it's going to go right there, and I know that I'm going to get negative, right? Omega 3, 3 over 2 times the sine of 60 degrees. I don't like it, but so VCM3X. We'll see in a second why I don't like it. It's a lot, this is a lot of fun, right? Sure. Just keep telling yourself that. 1.299, and these are feet per second. Well, not 1.299. That's what gets multiplied by omega. Sorry. So we can find what this is when we're done. I don't think this is correct. Oh, boy, that upsets me. But I'm leaving it in there. I need to figure out. It's got like a bit of a dilemma. Now I don't have enough room. I guess I can start it at least. And now we're going to go impulse and momentum. And we'll do the diagrams. All right, so it starts out like that. This is initial. And then we have impulse. And then we have final. Man, time is really running away from me today. Okay, so in here, the only thing we have the initial we have before the collision. This is before the collision, so this is MV, and I'll just call it MV2, right? And that's equal to 8.25, right? Now, the the impulse that's happening onto this, wait a minute. Well, we could say that the time is going to be so short that we're going to multiply that by the weight right here. But the integral of the weight dt is very small, so we're going to ignore it. Here, I'm sorry, I didn't mean to write f. I meant to write the integral. The integral of f at a dt, that's large combined, right? The force is very large even though it's got a small amount of time. So it does have an impulse, and we don't want to know it. So we're going to take the moment about that point is the thing we want to do. And for here, I have to make a decision. Okay, so I have the velocity of the center of mass going upwards, so I'm going to do that. Right, so here is m of v cm, and I guess go cm 3y, right? It's the y component of the thing. Here's the problem. Here's a dilemma that I have. I have this guy coming in that direction right there, and you'll see in a second why I have to say that I think this needs to be m3x, why I think that needs to be 0. and I believe it's going to rotate. Like so, it's gonna. You can picture this thing bouncing. It's gonna bounce, boom, and it's gonna rotate like that. So, and I'm just picking it as a default. All right. So in the x direction, let's just write this. All right. I didn't write out the main equation, but look at here. There's no momentum in the x direction. There's no impulse. Therefore, v c m 3x must be equal to 0. It's the only way that can. There's nothing that's making it go in the x direction. But I have this conundrum here, though, in my velocity diagram that is showing that I'm going to have an x component. So I don't know how to handle that, except to keep going and to question, how is that going to be possible? I don't know. I think this has me convinced it has to be 0. This right here says, well, it's gotta, so I don't know. We'll just have to leave it as a mystery to this world. Right? The source of the thing, which is an earlier edition of a Beer Johnson, does not factor that thing in. It doesn't. So anyway, here's one continued. And maybe you could figure it out for me. That'd be great. So we want to take for here. It's not gonna. We can't do the sum of the impulse momentum in the y direction because this is an unknown, right? In the y direction. So what we're left with is we have to do the sum of the effective angular momentums, right? So I guess I'll go I omega, let's call it 2, plus sum of m v2 times, and usually they'll be, these would actually be crossed. I'm trying to remember if we which order of operation is going to be in there, but it's going to be times the distance. I'm trying to think how my equation sheet shows this. Let me go back to the equation sheet that we use in class and have it at our disposal for exams. And yeah, right there. Okay, so we say crossed right there. Yeah, so crossed r g with respect to wherever we're taking it about, right? And then plus integral. I think it has to be integral. Integral of MO dt, and I'm not going to have enough room now to write the thing, but I'll go down to the next slide. Let me just move this over to the side. And summation of I about the center omega, and then this is going to be, this should have been 2 to 3, right? Because we're going for 2 to 3. 3 plus sigma m v3 crossed with r g with respect to o. Right there, right? So let's just use values right here. We'll start out with what we find right here. There's no rotation, but there is momentum right here. So there's m there, and we're going to treat counterclockwise as positive. So we have the mass times v2, right, times the distance, and now the distance from here, because we're going to take it about a. We actually should have said a, I think, everywhere in here. Yeah, that would have made sense. Yeah, so that's the point we're taking it about. We're taking it about A. So we can get rid of this. And this one disappeared because it was very, very small compared. Like the time is very, very small in the weight. Okay, and so this distance is going to be LAB over 2 and cosine of theta. Right? That's that distance right in there, right? Because this is the L over 2 right here, and here's theta right in there. So it's only that distance that's going to kind of create like a moment. And then you'll notice there's nothing right here, so that's going to be equal to all the momentum that's over here. And of course, I already said I've decided that has to be 0, even though the velocity diagram is telling me something else. But I don't know, maybe we'll go back and maybe I'll make a model of the thing. That's what I'll do. I'll make a model and solve it and see what happens. That's what you need to do in real life, right? When you're calculating something, you can't just trust the numbers. All right, so I didn't calculate this, but I know that it's 1/12 m LAB squared. Right? I'm doing this for a reason. Not I'm going to notice the mass is actually going to cancel out. And then one last one right here. This is going counterclockwise. This is actually going to go clockwise. So it's going to be minus m VCM 3y. I know, it's great. But now also times LAB over 2 cosine of theta. Did I do that correctly? I think so. So notice that mass cancels out. That's nice. All right, so we can start putting values into this. V2 was 8.025. We got that from right here. And L is 3 over 2 cosine of 60 degrees. Exciting. And then we're going to go 1/12 3 squared. I think that's right. Oh, we needed an omega in there, dummy. I don't call yourself dummy. Omega 3. There's a minus right there. There's omega 3. All right. Now minus, but we've got this guy over here. We already have him as our 4.815 minus 0.75 omega 3. Right? And then lastly, we have 3 divided by 2 divided by the cosine of 60 degrees. So we can solve for omega 3. And what I got was 7.337 radians per second. And I did get that it was going to go that way. So that's part of what we wanted to get. We also wanted to get we also needed the velocity at the center of mass. Here's the controversial thing. We could put it right back into here, and we can find the velocity of the center of mass 3y. It's going to be 4.815 minus 0.75 times our 7.337. And I said that comes out to 2.522 feet per second. If we were to plug in the other number, I didn't do it because I had for the x direction, which I don't think is correct, 1.299. That's pretty substantial. 9.53. That cannot be true. That's not possible. I don't know how that ended up in there. It's interesting. Yeah, because that velocity would not. That's like faster than the thing is flying down. So it's nonsensical. But I'm still just a little. Anyway, now I want to find the efficiency. And so a good place to start is like right up here, 1 versus 3, because nothing happened between 1 and 2. So it's going to be a lot easier to write like KE1 plus PE1 plus some more external thing. Now we're not going to know this, so we're just going to leave it alone. But I will point out to you that we have KE, but I said 2 and I meant 3. 3 plus PE3. Well, this is the datum, and this started from rest. So right here we have, so PE1 was, of course, MGH. And another thing we're going to find is that the M's are going to cancel out, which is interesting, that the efficiency didn't matter. The mass didn't matter in the efficiency. So let's just leave that for the time being as M, all right, and then go 32.2, and our H is 1 right there, right? So it's just 32.2 M. And then the kinetic energy at the end state is going to be 1/2 M v the center of mass 3 squared plus 1/2 I omega 3 squared. I'm going to leave the masses in there, right? So I'm going to go 1/2 M, and let's see, the velocity of the center of mass we decided had to be 2.522 squared plus 1/2 1/12 M L squared, which is 3 squared, times my 7.337 squared. If you put all of that together, what you end up finding is you get 23.37 M. So the efficiency is going to be the energy after the collision divided by the energy before, right? So it's going to be KE3 divided by PE1, or 23.37 M divided by 32.2 M. And we get 72.57%. So the answers for A, we're going to say VCM3 is going to be equal to 2.522 feet per second upwards. Omega 3 is 7.3, I guess it'll go 4 sig figs, radians per second, and that direction. And then for B, the efficiency of the collision was 72.57%. And we're done. Yes, I know, we're almost there. We're almost there. And if I had just a little bit more time, I would totally have made a SolidWorks model out of this. All right, so class is actually starting soon. This is a longer video